Okay, hello guys. Today's name's number 11, and we're gonna talk on some examples of symmetries, very important ones, and those are called functions and symmetries. Okay, so now we're going to see how symmetries that we talked a lot, how they actually display themselves, how they show themselves in mathematics and particular functions and their graphs. This is a very important thing to understand how it works, because when you understand it, will be much more easier for you to understand how the whole functions behave and all kind of things. So let's, for example, start from the simplest function, y equals x. Y equals x. Okay, what kind of graph would be this? First of all, before we start this, I'll tell about some other symmetry that I probably forgot to speak before. We talk about reflection symmetry, right? We talk about rotation symmetry. We talk about shift symmetry, like shifting. But we forgot about one thing that's called central symmetry. Central symmetry means that you have some point, and if you have a figure, so any point of a figure of a curve, right, should have the symmetrical on the same distance when you put the line through the center of the symmetry. So if you have on the plot, like on the graph, point A, you should have something 8 prime somewhere here. If you have something like here, like point B, you should have the same distance, point B prime here. Like for example, this kind of graph, it is central symmetrical. So each point, when you take like this point, go through center, the same distance from the center. You see? So this is central symmetry, called central symmetry. Very important one. Like the circle has a central symmetry. Many actually figures have central symmetry. You'll think about it, and we will talk about something like this today. Okay. Now let's start from this y equals x, right? Let's put number x's, or x and y, right? Like let's start from point 0. What do you think? Point 0, if you put x0 here, right? What would be the y in this function?
Y would be 0.
Y will be 0. So this point is exactly here, right? x0, y0. Right? That's normal. Now let's start maybe from point 1. That's point 1, right? And y will be?
Y will be 1.
Y will be 1, yeah, pretty easy. So here the point, and probably some points here, right? Like if you put 2, would be 2, it's easy, right? Somewhere here. And something else. What do you think, before we do the whole thing, what do you think, does this curve, whatever it is, does this curve have any kind of symmetry that we talk about? What do you think? We don't know yet the curve. Looking just here.
What are you looking at me, Katel? Look.
No, just look here, yeah. Y equals x, right? So, okay, it's maybe difficult to tell right away, right? So, let's think about it. Now we try just further approach. Of course, 3 will be 3, right? Let's try something else, like -1. What would be the y for -1?
What would be what?
For -1, what would be y? Huh?
That would be
-1, of course, -1, right? So the point will be here, right? -2,
2.
-2. So can you tell now, is there any kind of symmetry we're talking about here?
Yeah, like a reflection symmetry or something.
Reflection on what? Where's the mirror? Where would you put mirror to make reflection symmetry? Maybe just tell me. What do you think? Where should be the mirror? Maybe it's reflection symmetry.
No, I was thinking of something else. Maybe like. No, but I'm going to say it's reflection because it's different distances. Yeah, I don't think so.
You don't think reflection symmetry?
Yeah.
What else?
Well, there's rotation, but that wouldn't work.
Rotation, yeah. Rotation to what angle?
To 180?
280?
280. 180. To 180.
180, yes. So, yeah, with this point will go to what point then? If you turn this curve onto 180. To which point will go this point? 1 goes to?
-1, -1.
-1, right. Okay. And 2 goes to?
If I said rotation first. No. Yeah.
If it's rotation. So rotation 180, right?
Yes.
So -2, 2 goes to where?
2 -2.
-2, of course. -2, yeah. Okay, so we have rotation symmetry. What something else? Maybe we just talk about. Remember the symmetry we talked today. What do you think about it?
Central.
Is
Yeah,
it?
it would also be because there's like a center in the circle.
Here, yeah, against this point, right? This point goes to this point. This point goes to this point, minus, right? So it is central symmetric too, right?
Yeah.
And also, you mentioned mirror symmetry. No idea where to put mirror to make this symmetrical?
Wait, dot to dot.
Huh?
Dot to dot. No, it could be diagonally through the dot.
Through this dot, right?
Yeah.
And diagonal goes to where?
From the upper left to the bottom right.
Right. So if we put mirror like here, right? Looks like, so we have rotational, we have we have central, right? And we have reflectional symmetries, right, for this. And if we think about it a little, the curves would be pretty simple. It's be like this. It's a straight line.
Yep.
It's easy to see, right? Now, let's talk about slightly different. Y equals -x. So this is the curve which A equals x, right? Y equals x. Now -x. What would it be? Let's think. If x is 1, y is?
-1.
-1. It's probably here, right? Now, is x is 2?
I mean 2, sorry. Yeah. If x is... Oh yeah, that's true.
If x 2, y?
2. Sorry.
2?
Yeah, -2.
-2.
No, question.
So it's here.
Oh, you said 2, no, x equals -2.
And you understand, right, that this will be exactly this kind of thing.
Yeah.
So this is y -x. There are two lines, right? The very important lines, remember these straight lines, these curves for these simple functions, minus plus x, right? And you see that they are symmetrical. They are symmetrical against this mirror, right? Against x-axis and against y-axis. You can put mirror here, right? That's like reflects here or here, whatever it's still. And also, is it, of course, this the curve itself, it's rotational and everything. I'm talking about now two these lines. This line is symmetrical to this line. And how we do that? We put minus here, right? We put minus here. Now let's let's go a little further. Okay. Sorry. Okay, maybe just like maybe 1, y, x, right? Something like this. Let's talk about the curve y x to the power 2. Quadratic function. Quadratic. Take a look at this. It's a square thing, right? It's square. So if you put x plus with the sign plus, right? And the x minus, would it be the same y or not?
Same y.
Same y. So each point we put here will be with a minus x here, right? Plus x, minus x, right? So minus plus x will give the same y. It means that the curve will be what? What do you think? Each point here would have the same point here. Huh?
You had the same the like coordinates.
Yeah, same coordinates. And about what we can say about symmetry of this thing?
Rotation.
Huh?
Rotation.
Rotation. Okay, rotation.
Reflection.
Reflection against what?
It's like along the y-axis.
Not yes. Against. I'm not sure about term, but I think it's against y-axis. Okay, it's not along. It's like this. Against, like the mirror is here, right? So reflects goes from here to here, right, and back, right?
Yeah.
Okay, this is good to think. Good to know, because if we know how to put curve here, we know how to curve here goes, right? It's exactly the same, just reflected here. It's to make it much simpler to find the whole thing just by noticing that minus and plus will give you x. And now let's talk about maybe another symmetry. This is about symmetry against y. For seeing symmetry against y, we change signature in x, right? If we want to look at the symmetry against axis x, what do you think? Where we should change sign?
I don't know.
Just think. We change x minus to plus, right? Or plus to minus, right? And we have symmetry against y. And if we were talking about against this axis.
Yeah.
Now we have axis x, where we should try to change signature to see if there are any symmetry against axis x.
I think you should change the y.
Exactly. Y. Let's try here, right? We change y to minus y. It will be. Would it be correct? What do you think? X squared is always more than 0, right? More or equal. It cannot be negative. And
Yeah.
minus y easily can, right? So there is no symmetry against x. That's how you look into it. Okay. So this is not good for us. But anyway, we know that it's not symmetrical against this x. Okay. So it goes somehow different. Now let's try to put the curve, right? How it goes. Okay, we can do only this point, right? So 1 would be equal to, if x1, y will be
Would be 1.
Will be 1, yes. It's here, right? Now for 2, y would be
Okay, y would be
2, x2. 2 squared, come on, mathematicians.
Or 4.
Yeah.
Oh, x is 2. I was thinking.
Huh?
Yes.
Yeah, sorry, 4.
4, okay,
I
sure.
was thinking like
4.
Thinking something else. I don't really get it. No.
And for minus, of course, the same symmetrical, right? So it would be 1 and 2, right? Would be here and here, right? So symmetrical. 2 point here, point here. Now about okay, which one? Like for example, 0.2.
Yeah.
So somewhere here, right?
It's 0.2 squared.
0.2.
Oh, okay. Oh, that means y is 0.4.
Huh?
Y is 0.4.
And by the way, let's put here the line too. I would just put the line y equal x, right? Just to look how it looks like. So
0.04.
yeah. So how it will be?
So y would equal 0.04 then.
0.04, right? So it's very small, right? Very small here. 0.04, right? And this is, so it will be somewhere here, and the symmetrical point will be somewhere here, right? So we see here, here, and here. So the curve will go like this, and goes up and up and up, right? Up and up and up. And you see that it intersects with the a equal x in the point 1, right? And because it is symmetrical, reflection symmetry against this curve, this axis, it will be the same thing here. So we have the curve which is symmetrical against this axis, reflection symmetry against this y-axis, right? Now let's try another, which is named x like to the power 4. If x 0, y is?
Wait, x 0.
0 the same, so here is the same point, right? If x is 1, it will be 1,
Y is 1.
right? If x is 2, it will be
14. I mean 16. Yeah.
16, somewhere there, right? Somewhere higher there, right? And now for example, I don't know even which is the best. Okay, let's try 0.9.
Wait, 0. Oh man. It was 0.81, and that's times. And that's times 0.
81? 0 point?
No, I'm thinking talking twice over. 81 over 100, just 81 over 100. I can't do that in my head. I'm not as good as Vita. Did you just say 81 over 100 times 81 over 100? No. Vita.
Do it like this.
It's 0.9 quadrupled. Oh, 0. I can do that in my head. I tried.
What's 9 squared?
81.
Divided by what's in the bottom? Take a look.
Oh, 100. That's 0.81.
So tell Jada.
0.81.
And squared, because this is 4, remember?
Or something over 10,000.
Yeah.
I can't do that in my head. That's 600.
So a very small amount, right? Somewhere here.
6,400
It's actually-
divided by 10,000.
How much you said? Tell me again.
0.064.
Point
No,
zero.
0.64, sorry, 0.64. Is it 0.64?
No, Papa, it is 0.0064.
0.064. It's there are 4 zeros here.
Like a
Yeah, 0.064.
Yeah.
Approximately.
So it's somewhere very close to 0.004 here, right? So just a little here. So here we point. This point. You see the curve goes lower here before 1, lower than the previous, right? It goes somewhere here, but then it goes like very fast, to 16 and very fast. So it goes like this. Somewhere, no, just more like this, right? And the same here, you go like this, Symmetrical goes like this, right?
We.
I'm sorry. Here's the point. So we see interesting feature. First, it's symmetrical, the same as this one, right? Minus to plus x minus to plus gives the same y, so it's symmetrical. You can see it from the beginning. And now this part is before 1, it's below line y equal x, and here it's above y equal x, and above the curve x squared. It goes much faster up. And if you put some more, like x to the power of 8 and everything, it will be easy to understand. It will be even lower here because there are numbers less than 1. Much lower here, but much higher goes here after the x equals 1. So this is for x2 and x to the power of 4. Now let's try something else. In the middle, x to the power of 3.
Oh no.
What do you think, first of all, about the symmetry of this thing? Okay, if we try x to minus x, change x to minus x, so it will be plus x, right? And we change to minus x. What will happen with y?
Well, why would have if x is negative?
If x
Why would have? Yeah, but it's positive at y.
here, see here, y is not changing its sign. Here and here, y is still positive. Whatever x is x plus or minus, right? And here, if you change x to minus, y will be
minus then.
minus, right? Minus. And this means, remember what happens with this thing? When we change minus x, x to minus x, y change too, and it will cause what symmetry? Remember?
Reflection.
Reflection against this, or central against point 0, right?
Yeah.
So when you change argument or x, let's call argument, to minus, and the result will be changing the minus to the minus 2, it will cause central symmetry, and the curve will go somewhere in between here and somewhere in between here. So slower going than x to the power of 4, but faster than the power of 2, right? And here it goes like this. Central symmetry. Look, each point here corresponds to points here against this point 0. And the same thing if you think about it, like for example, x to the power of n, right? X to the power of n. If n is, how it's called, odd and or
Odd evens.
Odd and even, yeah. If n is odd, it means what symmetry?
It could still be positive.
Hmm?
It could still be positive. Oh, symmetry.
Symmetry. What symmetry will be in y equals x to the power of n?
I still. Oh wait, no.
For odd number n. Is 3 odd number?
Yeah.
Okay. So for this, with n odd, it is, what symmetry it is?
What's reflection be this on? It'll be positive. No. What reflection? Negative. Rotation. I mean, pizza. No. What's symmetry?
What's the other type? Odd and what? Even.
Yeah, or even.
For even, okay, let's go from opposite. If we have even, n even, so like 4, 8, whatever, when we change x to minus x, would it be, the y will change sign or not?
Is it? Oh yeah, that means it's or am I doing that wrong?
No, yeah, it will not change, yeah.
Yeah.
Because when you do it with the even numbers, 2, 4, 8, 6, whatever, It will not change. The y will not change. And so with even we'll have this reflection symmetry, right? Reflection against y, right? And with odd we have the same as here, central against point O, central. So for all odds, so you see the symmetry. If you understand the concept of symmetry, how to use it here, you know, it helps a lot to take to understand what kind of graph it is, what kind of function is it. Like, for example, is this Antosha? What's the called this function, by the way? Not polynomial, but what?
Which?
Huh?
Which function?
This x to the n to the power n.
Well,
Степенные in Russian.
it is a polynomial.
Polynomial. Okay, it's simply polynomial. Okay, we'll talk at polynomial. So polynomial.
Quadratic cube.
Polynomial. Okay, let's say polynomial a little more generic, but anyway, it's a type of polynomial. Okay, now let's go a little further. Very important curve.
Toma, can you bring the thermometer?
Antosha, remember I am recording.
Oh, I'm sorry.
Yeah. So, okay. So let's try to do this. Let's look at that kind of thing. That kind of function. It's a little abnormal. It's not y equals something, but this is some equation which actually corresponds to some curve too, some graph. And we have to understand what kind of graph is it. What do you think? X squared plus y squared equals 0. It's an equation, so it should have some solutions, right? So some x and some y, which actually good for this, which gives you this this equality.
Well, x and y would both equal 0 then.
Equals 0. Something else? That's good. Can anybody else?
That means they'd be stuck in the center.
Complex numbers.
Okay, come on. We're not there yet. Okay, but okay, yes, there is solution in complex numbers. Remember this I, quaternions and everything, yes, I, G, K, but we are not talking about it yet. Okay, we're talking about regular integers, right? So do we have any solutions here except x equals 0 and y equals 0? No.
I don't have anything else.
No. So just x, and so the whole graph for this interesting function, it is just 1.0. That's all. Sometimes, like in physics, I don't know, mathematics maybe not, it's called the degenerate graph. So just 0. Now let's talk about a little more interesting, like x squared plus y squared equals 1.
Well, x and y equal 1, so it'd still be 1 point, but different place.
You think so?
Yeah.
Let's talk about first of all, maybe not, but we can talk about symmetries first, right? For example, if we change x to minus x, would it be the same or something? Same.
Same.
So this plot should be symmetrical against what axis? If you x.
Oh, what?
Reflection symmetry against what? If we change x.
Oh, it would have against the y, I think.
Against y, yes, right. Against this axis. Now let's try y change to minus x.
It would just be stuck in one place.
So would it change if y changed to minus y?
Well, it would change. It would still be the same thing.
The same. Yeah, it is the same.
Same thing, but
Yeah, same thing.
it would just be one dot.
No, it is the same. Yes, it's right. It is the same. So if it is the same, that means that when you sorry, not minus x. Sorry, I just put some wrong. Y to minus y. Yes, y to minus y. I'm sorry. Y to minus y. So y to minus y will be the same, right? So it means that this graph will be symmetrical against what axis? If you y.
Oh wait, no.
Yeah, correct.
Oh yeah.
X. Yes, x. Mm-hmm.
Yeah.
Correct. Against x. So this graph will be symmetrical against y reflections and against x reflections too. Now let's do both. Change x to minus x and y to minus y together.
I think
Hmm?
it would be the same. I think.
Yeah, of course. It will be nothing will be changed, right? So you took minus here squared anyway. Minus will give you plus anyway. So even if you do it together, still will be the same plot. It means that it is not only reflectionally symmetrical, but also what symmetry gives you when you change both?
Central?
Central. So it is reflection x and y, and it is symmetrical against 0. So we know a lot already, right? So each point we put it, the same point will be here, the same point will be here, and the same point will be here against the point 0. So we know already, we can find one point here, we find the same points in the other quadrants. Quadrants, right? If I'm not.
Quadrants.
Yeah, quadrants. So this is first quadrant, second, third, and fourth. So we know already a lot about this curve, and we don't plot it yet. So let's think about something else. If you look at this thing, does it resemble something? Maybe you can find out in your memory something that look like this. Don't remember any theorem or whatever you heard about it before?
A theorem that you have proved yet?
Yeah, may have proved, right?
Say.
Yeah, the Pythagoras theorem.
Pythagoras theorem, yes. So it means that x and one side, right, of triangle, y another side of triangle, right? And 1 is the square of hypotenuse.
Two legs and a hypotenuse.
Yeah, legs and hypotenuse. Right.
So hypotenuse is always 1, but the legs can change.
So it means that if we put the triangle here, right, we'll have like this, which is equal to 1, right? And here is x and here is y, right? And whatever x and y are, squared plus squared should give you 1. What do you think can be, so distance from point 0 to some point on the graph would be always 1. What kind of curve can it be? What do you think? If the same distance from the point 0, whatever x and y are, what do you think? What kind of curve can it be?
What am I drawing here? Look. What's this finger? Look at this.
Let's try two things. Like first here 1, right?
When you're taking
And here 1.
180?
And here 1.
it looks like
Minus 1. It's also symmetrical, right? So here,
Did
here. Oh,
half a circle?
yeah, it is circle, right? Because radius of a circle is always 1. So it's a circle with the radius 1. And it is, of course, symmetrical against this axis, symmetrical against this axis, and central symmetrical, right? So this is a very important thing. This is the equation of a circle,
Oh yeah.
and you can put r here, which will be r here. Not 1, but any.
That makes sense.
R square, sorry, r square. Usually square, because this is, remember, Pythagoras theorem, right?
Yeah.
Should be r squared, the hypotenuse, right? So this is thing. And triangle here is this for each point. This, and this is hypotenuse, right? This. How you said legs, right? Legs.
Legs, yeah.
Legs. This like that. So, okay. With this curve and this situation, a very important thing is connected, which is called trigonometrical functions. Trigonometrical. And they go like this. We denote this angle like phi, this angle. And there's definition that if you have some phi, right? So this this leg, right? This leg, so the y, the leg with the length y, right? It is called sine, right? Sine of the angle phi, and equals y divided by r. And the other leg, this one of the same triangle, we're talking about still the same triangle. The other leg, it is called cosine of the angle phi, and it is x divided by r. If r for r equals 1, sine phi equals just y, and cosine phi equals just x. This is a definition. This is a definition of functions, actually. And they are very important in it's called so-called trigonometry, the science that it goes about triangles, how to define the different sides of triangles, and a very, very important thing is mathematics. So sine phi and cosine phi. Now, if we have sine phi and cosine phi y and x, we can easily see interesting relation between sine and cosine. If we talk, when we see that this is the triangle, right? This right triangle, those are legs, and this is a hypotenuse of right triangle. And the radius is 1. So what do you think it is, this relation? If y is sinus and sine and x is cosine, what can we do? If we put it here, so x squared plus y squared equals 1, radius is 1, right? And x is cosine, so we have cosine phi, cosine squared phi, sine squared phi equals 1. We just put y and x from here. And this is the main formula of trigonometry, equals 1. Cosine squared plus sine squared equals 1, always.
Wow.
Yes, so you see how powerful is symmetry and the Pythagoras theorem, right?
Did you explain what a sine and cosine were? Oh yeah, you did. Yeah, there.
I explained. Those are definitions. These are definitions. So you may write it's definitions of cosine and sine of this angle phi. And interesting enough that if you change r, these things will be still the same. So this is very powerful definitions, very powerful things to go. Okay, so just for example of a little different thing, but with all this. Any questions, by the way, on this?
No.
No?
I get it.
Remember, there was an example of something else, because Pythagoras theorem is about Euclidean geometry, right? So where like y squared like x squared equals like something, right? R squared. But in another geometry like Minkowski, which is very important in like theory of relativity, there's another situation. Is against instead of y there is t, which is time. So t minus t squared minus x squared equals tau squared. This is tau.
Tau.
Greek. Tau. Tau.
Tau.
Tau.
Tau.
Tau. Yeah. Why tau? Because in Minkowski, this is just an example. It's just to think around. Tau stands for so-called proper time. So the like real time of the thing. If you travel somewhere, this is your real time. This is the time on your own clock. You travel somewhere, right? And you can, for example, you do, I don't know, did I write it or not? So tau means for real time. So if you do square, if you find out, you will see this thing, minus x squared, right? And you take t out of the root, we'll have t 1 minus x squared divided by t squared.
Can I ask you a question? In the original formula, is it t squared minus x squared?
That's maybe this way or that way. This is original form because tau considered to be how to say real number.
Is the
If you
is x squared?
Huh?
X, is it squared?
Oh, I'm sorry. Just I missed. Yes, of course it's squared.
Okay.
Of course. And x divided by t squared, it is actually speed, v squared. If you measure time in seconds, and distance in so-called light seconds. So distance is how much speed goes by second. So it's x light second is 300,000 kilometers, because per second light makes 300,000 kilometers. So this is one of the main relations of theory of relativity, which if you look at this, if speed equals 1, so 1 light second divided by 1 second, it's just 1 divided by 1, so 1 equals 1. Here we have 0, and tau is 0. So if you go with the speed of light, this formula gives you exactly that no time has passed for you. With the speed of light, you can reach the end of the universe with no time. And interesting enough, just for you, for example, I will write interesting plot of this particular thing, not this, but this. And it looks like this. It's t, this is x, and this is the curve, which is called hyperbola. It is, if you look here, right, it is reflection, it has reflection symmetry against x, right, and central symmetry. There are two these things. And this is tau squared. So this is tau, not squared. This is just tau. This vector to here. So that's how it looks like in Minkowski, not Euclidean geometry. Okay, guys, any questions?
No. Oh wait, I have a question. What is x?
Huh?
What is x?
X is just distance. You travel to the distance x. If we measure if the distance in light seconds means the distance that light pass, when it travels with the speed of light.
Yeah.
So light second is exactly 300,000 kilometers actually. And t in seconds, the v will be when v equals 1, it equals the speed of light, because speed definitely just by definition. So that's these units of measurement. They are often used in theory of relativity. Just makes c speed of light equals 1 when you do that. Okay, else?
No, I don't know. I know.
Okay, guys. So think about symmetries, and now I will give you some questions, right? On this.
I need to change my pajamas.
Wait. Stay here.
And I need to take a look. Then a little. Okay. So you saw the plot like this, right? I shown you. It's called hyperbola, by the way. Hyperbola. And think how may look like the other one, just opposite to this. This is the first question. How the graph may look of this thing. Using your symmetry ideas, look what kind of symmetry is here. Remember this hyperbola, right? It's like, looks like this and that, right? And this is, by the way, these lines actually, it's because y equals 1, it's exactly the speed of light lines. And these hyperbolas are of this curve, right? This curve. So this curve look like this. Think how this curve can look like. Using the symmetries. Using the symmetries.
Minus t squared.
X squared minus t squared equals tau squared. And I gave you the graph of this. So
right.
this
And
is
variables are x and t, of course.
okay. Now the same thing for this. Try to plot again symmetries and how look like this graph may look like.
Okay.
Just
and the
work
variables
on
in number 1 are x and t, right?
Oh, sorry. That's yeah. Maybe xy, maybe xt. Yeah, whatever.
Okay.
Xt, yeah, because I use tau, right?
Yeah,
So
yeah.
And
X times t equals tau. Okay.
okay, and the third, I think Antosha, you may explain, and you may work together with the kids, right? So how to plot this sine, cosine, and sine phi plus cosine phi. The plots for this, it's equal to y, right? It equals y. For example. So it's just a graph. So think about it and try to plot using symmetries mostly. Using symmetries, just try to find out what kind of symmetries are here, there, here, in this. By the way, this I can give you some clue. It may have a shift symmetry. This one, because phi is the angle. It goes circular.
Okay.
And it's 2p. Okay, that's it, guys.
Thank you.
Okay, see you next time, guys.
Tito, can we see Babu?
You want to? Okay, just a second.